my last kick at the can with you here before I turn things over to Leon will be to try to then complete the CNP story by talking about P a bit. Microorganisms compete, as we've been making the case, with each other and make that competition successful because they have an ability to get the food or the energy that they need. That's a fundamental principle of any microbial selection, right? Is that there's always microbial competition, and whoever gets what they need to their satisfaction wins the game. And winning the game simply means I get to have a family. And those that can't keep up don't become a part of the contributing microbial ecology. So it's all about energy availability, but in phosphorus removal, it's largely about energy uptake and storage. Okay, so we're going to talk a bit about the storage function. And I'd like to begin this by saying, try to relate things to ourselves and our own physiology. What is the energy source that runs around through our blood supply that provides energy moment by moment to our cells? What do we live, what's the sugar that we live on in our blood? Glucose, exactly. And it's vitally important, and our bodies really try very hard to maintain a steady state glucose concentration and circulation, right? And so there's kind of a range of glucose that, and for perfect physiological health and balance, it's really being maintained right there. The engines always, all the cells are getting the energy moment by moment they need because the glucose is always there in supply. Now we also know that if we consume, and I'm not preaching to you about diet, but we know that we consume foods, and what our body does is it really tries to get whatever we get converted into the form of energy that we can make, that it knows how to make use of. And so a lot of things that we consume really get very quickly converted into glucose. And then, of course, we have different systems for managing that glucose inventory, right? A lot of that goes on immediately in the liver. And of course, we know that insulin is playing a role in managing the handling of the glucose through the cells and so on and so forth. But where do we store? So all of that said, the molecules of glucose that the liver is handling, then only a very small amount of that actually is needed in the blood supply moment by moment. It's trying to manage that. So the liver is trying to titrate that out to the blood supply to keep it within a healthy, not too much because that's a problem, not too little, that's hypoglycemia. The liver is managing that. But there's a whole lot of that glucose then that has to be handled some other way. And this is not to go back to medical school or anything like that, but it is to, there's a method to my madness here. Where does our body put, or how does our body store that glucose that it doesn't need for the moment? It can go to fat, yes, it can go to fat, but the first place it goes, and it's supposed to go, and it does go, and it's in the liver, it's in the muscles, it's in many cells. Anybody got an idea of what that storage, where the big energy sink is? What is it? It's called glycogen. Have you ever heard of glycogen before? So glycogen, what glycogen is if you take the glucose molecule that the liver made, which is 6 carbons, and you start hooking those together We call that polymerizing it. You make a glucose polymer. If you put about 30,000 of those together and you wrap it around a little protein core, you have a molecule of glycogen. It's a packet. It's a high energy packet. And we pack glycogen away, and thank goodness we do, because we put all of that glycogen. The liver is just packed with glycogen. Our muscles are packed with glycogen. And when we need glucose between meals or for whatever reason, there's a very easy extraction. It just takes that glycogen and it pulls the glucose off and it sends it off to the bloodstream. If anybody's ever done endurance athletics or watched endurance athletics, particularly something like the marathon, there's a condition that people run into or experience in endurance events. Sometimes they call it hitting the wall. It's a point at which the body actually finally depletes all of the glycogen that's in our muscles and in storage. And it literally is as if you ran into a wall. You shut down. As, you know, you'll see people running along, and the next thing you know, they're walking or they're on the ground because everything shut down. They run out of energy, right? So I'm telling this story about glycogen, one, because I think it's just interesting to know stuff about ourselves, but secondly, in the phosphorus removal biology, there is competition between competing microbial species for energy and energy storage. And yesterday I introduced the concept, in fact, I talked about GAOs and PAOs. And I said that GAOs were glycogen accumulating organisms and PAOs were phosphate accumulating organisms. And both of these organisms are present in our wastewater ecology. And they're both trying to get the energy. And what we're trying to do is have the energy molecules that are going to be taken up and stored by the bacteria go to the ones that do the work that we want them to do. And the work we want them to do is to basically remove phosphorus for us, please. You know, we're trying to get bacteria that have that special ability to take up and store phosphorus. And where the glycogen piece comes in is the energy the cell needs to actually do this phosphorus transformation is from the molecules that also could be taken up and be converted to glycogen and robbed of the phosphorus accumulators by the glycogen accumulators. In other words, there's bacterial strain that wants to eat the lunch of the phosphorus accumulators, and in doing so, it makes the phosphorus accumulator less competitive. And when we have an overabundance of GAOs, we have lower PAOs, and if we have lower PAOs, we have lower phosphorus accumulation. So we're trying to understand then how to enhance the conditions to grow robust PAOs. And part of that is just understanding that there's a competition that's going on with a species that lives in the same, it's riding in the same bus and it wants to eat the same sack lunch. And there are subtle things that give it that it doesn't like so much that we want to use against it to feather our nest. So that is my little bit of digression to get into the topic here. This is all about energy uptake and storage as much as it is phosphorus manipulation. Okay, so I hope that's helpful as we go through this. Phosphorus removal ends up being a two-step process where we're actually going through an intentional phase where we're asking the bacteria to release phosphorus and then eventually take it back up, and we establish that by alternating anaerobic and aerobic conditions. So this is there's a real there's kind of a metaphor here of a metabolic switching gear that's turning on and off, uptake and release, uptake and release, uptake and release. And that is intentional for these phosphorus accumulating bugs. They, remember I showed you the fluorescent in situ hybridization techniques for visualizing by fluorescent tagging. So this is just a fish probe showing you this Candidatus cumulobacter phosphatus, a very common PAO. It takes up, in this case, a blue tagged fluorescent dye. So you can see the PAO is a very significant part of that particular flock. So, we can find them by different means, but one of those is this fish technique. Under anaerobic conditions now, and I'll just call them PAOs now and not give you the Latin names for these things. So the PAOs are readily hydrolyzing, or they're hydrolyzing readily degradable BOD. It's the low molecular weight, readily degradable fraction of BOD or COD that is the important point of their feeding cycle. They handle very small molecules of low molecular weight, and these are what we sometimes will call then VFAs, volatile fatty acids. You will see it as VOAs, volatile organic acids. I'm using them interchangeably. And these are low molecular weight, 1, 2, 3 carbon compounds. They are small enough that they go immediately through the semipermeable cell membrane, they get into the cell, and they're easily handled. So they take that up and they store it by taking those small little 1, 2, 3 carbon units and hooking them together or polymerizing them. And they make a compound then, or a nugget or a packet, whatever you want to look at that, of what we're going to call now PHA, polymini hydroxyalkanoate, or you'll also see it in the literature as PHB, polyhydroxybutyrate. That's polyhydroxybutyrate is a type of polyhydroxyalkanoate. These are different, slightly different organic molecules, but they're all in the same family, right? So we're going to use PHA or PHB interchangeably to mean these are polymers of carbon storage, high energy molecules that the PAO has taken in and stored up. It takes energy to do that. This stuff doesn't just leak into the cell and magically hook together. That bacterium is investing energy to make that happen. It's actively transporting material across the membrane. It's actively forming chemical bonds that takes energy to do that. Where it gets the energy from them to make PHA, to make the granules, is by releasing phosphorus, because it also has on board a phosphorus polymer that they sometimes call a polyphosphate. It's actually it's a battery pack that's full of energy. And the bonds, the energy, of course, is always in the molecules that are holding that energy. And so when we say energy is released, we could also say bonds are being broken. In other words, molecules have to be changing to release the energy that is holding those atoms together, right? So the release of phosphorus occurs because phosphate bonds, high energy phosphate bonds in that polyphosphate are being broken down to give up those electrons or that energy to make ATP to fund this thing. And when those polyphosphate breaks down, it forms orthophosphate, which is soluble and it leaks right out of the cell. So you take it from a polymer of phosphorus to a little molecule of phosphate, orthophosphate, and it leaks out of the cell. So you're getting uptake of carbon and release of phosphorus. And it's all about taking in something that stores up a bunch of energy, but we pay the price with energy from a different source, okay? So there's an energy balance there. Volatile fatty acids then are the building blocks of this PHA. They're high energy carbon polymers. So if you think of a simple, readily degradable, soluble BOD or COD, if we went to the grocery store, well, actually, let's do this. Let's take in the fall, we pick up a basket of apples and we take them over to our little crusher and we crush them down and we get the juice and we put it in a jug and we let it sit. What's it turn into? Well, it can turn into alcohol. If it's doing that, yeah. Somebody said vinegar. It's exactly right. What's vinegar? Vinegar is acetic acid. This stuff, that's acetate. So when we say a BFA, think just plain old vinegar. That's what it is. I put sodium acetate in here. That's really the salt of vinegar. So it's a common weak organic acid. So common stuff. This is what it looks like if you draw it out. This is the stick figure of it. There's the two carbons. These are hydrogens on there. This is the carboxylic acid. This is what makes it the acid part for those organic chemists in the crowd. It's a simple organic acid, right? What the cell does is it'll take 1,000 or more of these and string them all together. That's where the poly comes from. Poly just means many, right? And it's an alkane, right? So it's a polyhydroxyalkanoate. This picture on the right is an electron micrograph where they've actually taken a slice through bacterial cells under extreme magnification. So you're looking at a bacterium that's kind of the shape of a sausage, and these clear areas that are in the middle here, those are the PHA granules that are actually inside the cell. You can see that it's a significant part of the volume of that cell is that storage of the PHA. Okay? So this stuff is not imaginary. This is real. Now here's the glycogen part, because these bugs are also, they're not just making PHA. They also do exactly what we do. They make glycogen. So glycogen then is a polymer, like I was saying, like 30,000 units or so are hooked together. This is one glucose molecule right there. There's another one, there's another one, there's another one. In other words, they're linked together. So when we're saying a polymer of glucose, basically you've got this molecule strung together and it gets wrapped around. So each one of these little green dots is representing then one of those glucose molecules, and it wraps around a protein core. So this is what glycogen would look like. All of these are glucoses. There's the protein core. So when we talked about we're storing up glycogen in our cells, or the bacteria store up glycogen in their cells, they've made that. That takes work, right? There's energy that has to be invested to assemble something that complex. So there's energy required to build that, but there's a whole lot of energy that comes back out once you take those glucose and you put them then through electron transport and get all the ATPs back out from it. Now, that was the theory kind of what's happening molecularly. Let's look at it in the treatment system. So this is Cruz's system. We're looking at the one train anaerobic reactor looking downstream into the aeration basin, and the secondary clarifiers are going to be beyond that. Okay, so this is the anaerobic part of the system. If we take just one PAO bacterium, this phosphorus chelated organism, in this zone, the volatile fatty acids, the acetate, the propionate, the butyrate, are being taken up and they're forming the PHA. Okay, so they're polymerizing those little 1, 2, 3 carbons into many thousands of carbons. And the energy that it took to do that came from polyphosphate that they had on board, and so phosphorus is being leaked out as orthophosphate. So this is what we call phosphorus release. Right? It's carbon uptake, phosphorus release. If we look a little bit more deeply into what's happening in the cell, then going to make this a little bit more complex, is in that anaerobic cycle then, again, we have the VFAs, the volatile fatty acids, that are coming in to make the PHA. Remember that takes some energy. Remember, the cell gets all of its energy from ATP, so it has to have ATP. So ATP is coming into play here. The cell is bringing in ATP to fuel or to provide the energy to do that work. There's other branches in the metabolic sequence that some of those VFAs can go through. This is showing TCA, that stands for the tricarboxylic acid cycle. That's a primary mechanism also for ATP generation for cellular respiration. And that's generating other compounds. In this case, it's showing NADH2. That is part of the electron transport control, if you will. So it's an essential part of handling the electron. So, you know, I'm making this thing a little bit muddier or more complex, just say that there's a lot going on here. But what I wanted to show you is that in this PAO is glycogen. In other words, they've got glycogen also as an essential part of their storage, just like we do. If we didn't have glycogen, we'd be in deep trouble because we'd run out of energy very quick. So they also have a glycogen storage on board that is donating or giving up organic carbon to fuel or to fund the more production of ATP, and also to form the PHA. So that's the anaerobic cycle. Once we get over into the aerobic zone, then some other magic occurs. They had that PHA is where they took away all of their energy. Now they're going to, under aerobic conditions, burn it up, and it burns very efficiently, carbon dioxide and water, byproducts of respiration. So they're taking up oxygen, burning off the PHA, and this gives them great competitive advantage because all of those calories, or all of that VOD, however you want to express the energy part of the equation, that they stored are calories that wasn't available to competing other bacteria. They got it because they could take it up in that anaerobic zone and store it. So they got the calories now under aerobic conditions. They're burning that off. Well, they burn it off, and let's see, they're burning, every time you burn it off, they're burning it off for one reason, and that's to produce energy to do something else with. And the energy that they produce, again, it's going to come out as ATP. And that ATP then is going to power something else. And what it powers is the bug's enzyme pathways that say, give me your phosphorus now. Give me all of your orthophosphate because I can take that in and I can stick that all together because I've got the power to do that from the energy that's liberated from burning off the carbon. And it can't help itself. Once it gets started taking in phosphorus and building phosphorus, this polyphosphate, it builds a lot of it. In fact, it takes up every molecule it can find. And this is what we call luxury uptake. Sometimes they'll take up far more phosphorus than they have a physiological requirement for to build cell matter out of. What they're building is a nugget full of very high energy phosphate bonds. Then that will be utilized when they go back over to the anaerobic zone and want to repeat the cycle over again. Okay, so we're tucking in a lot of phosphorus into the cell. And this is then that more complex equation that shows under aerobic conditions, right? The PHAs, where they store their food, is burning off, converting to carbon dioxide and water. It's showing under aerobic conditions, they can put a bunch of it into storage like we do into glycogen. They're putting a lot of it into, a lot of ATP into the formation of polyphosphate, and they're putting some of their energy into cell growth. So it's like win, win, win. This bug is exploiting the fact that it had all of that energy potential on board in the form of polyphosphate to drive its competition. Took the carbon that other organisms also would have. I'll tell you what, almost every bacterium in the book would take those VFAs and eat them just quick as it can be, but not all of them can do it under anaerobic conditions. See, that's the trick, is that the PAOs can take it up and store it under anaerobic conditions and make it non-bioavailable for other organisms that would just love to eat that stuff. So away you go. So overall, then you've got these alternating anaerobic and aerobic conditions. There are denitrifying PAOs that they have found now that have complicated our understanding a little bit. In that, as I first learned phosphorus removal biology, there was kind of a dogma that said, in order to create the most ideal phosphorus release in an anaerobic zone, we need to have an absence of nitrate, because the nitrate will kind of poison the phosphorus release part. And I believe that's still sound science. And if I was running a BNR plant, I'm thinking of West Bank here, the West Bank modification there at Wilson Creek, where we do have nitrate scrubbing ahead of the anaerobic zone and so on. I think that's really sound, and I'm certainly not arguing against any part of that. What I'm trying to also explain is that there are PAOs that have been discovered that can actually do phosphorus accumulation and do it under anoxic or with nitrate in there. They're not as efficient, is kind of one of the points. They're not as efficient, but there are denitrifying PAOs. It's like, oh, crud. Just as soon as you think you learn it, they put another chapter in the book, and now it's even more confusing. But for all practical purposes right now, I think it's maybe best to just think of it in kind of the tidy sense that we want anaerobic conditions for phosphorus release and aerobic conditions for phosphorus uptake. Dan?
I have a question.
Yeah.
The microorganism has long chain poly in it, right? Coming in from the grass, right? Into that zone, that anaerobic zone. Now it's going
I want to not answer that right now, but I want to, but I want you to have an answer that's better and more complete than the one I'm going to give you, because, and I'm going to ask Leon to address this completely, because one of the things that Leon is very conversant in, much more than I, is actually, because you're talking about in the RAS line now, there's actually ways that people are doing RAS fermentation to enhance the phosphorus removal cycle, which adds another wrinkle into our dilemma here, or our question, right? It makes the question a little bit more complex, because normally we think of whenever it goes anaerobic, now we're going to have phosphorus release, and we're getting into trouble. And Leon has a trick, or I shouldn't characterize it as a trick, I don't have the right word for it, but there is a process that is sound science and it works, where they're exploiting RAS fermentation to improve phosphorus removal cycle by getting VFA production out of the RAS that overcomes the release that you would have gotten. These glycogen accumulating organisms are living in the same world and then traveling in the same short bus as the PAOs. And when they are competing well, they cause what we're going to call suboptimal, it's not working as well, performance. EBPR, enhanced biological phosphorus removal. That's just kind of some of the, the alphabet soup is crazy. We need magic decoder rings to understand this stuff, I think. But essentially, it's the competition issue again. And what favors one over the other then comes down to, this should look familiar initially, because we talked about growth pressures. We talk about temperature being a growth pressure. We talk about pH being a growth pressure, about the carbon and the carbon sources being a growth pressure. Oh yeah, those 8 growth pressures always seem to come back and keep defining the ecological niche that turns the corner on the BOD removal bugs, the nitrogen removal bugs, and now the phosphorus removal bugs. So we'll never escape understanding those growth pressures. So we'll consider that. But these are species that, in this particular case, there's a fish probe where they found that particular micropruine, a species that's a fermentated GAO that likes to take up VFAs, just what our POs want, takes up the VFAs, and it makes glycogen out of it really, really efficiently. It tucks it away, makes glycogen, and it's happy as it can be. And it doesn't do anything with phosphorus uptake. Doesn't need it. So the fuel that we needed for the PO to do the phosphorus uptake gets robbed by these guys that live in the same place and really they're going, it's Friday night football every night. These guys are going for the same football. Temperature then tends to play a role by cooler tends to be better for the PAOs. In fact, at low temperature, they dominate. So the GAOs are tend to be warmer bugs. There's, of course, who among us can control the temperature, right? I mean, it's sort of like, well, we're saying temperature matters, and by the way, you can't do anything about that. There are times when that is not going to be anything under our control. But at least knowing that is something to be kind of on the lookout for. If we're having a decline in performance, then keep that one on your checklist. Higher pHs on the slightly alkaline side of neutral is more favorable to what I call the good guys. I'm sure that the GAOs do not appreciate being then categorized as the bad guys, but will suffer their wrath, I suppose, by putting them into camps. Competitive advantage goes to PAOs at higher pH. Carbon source is also interesting, where you have a mixed bag of carbon sources, meaning that not just all of one flavor. So acetate and propionate, for instance, as a mixture would be more preferable for growing PAOs than having a single source carbon source where they're just feeding them one straight thing. Dan, I can't remember, do you guys have a fermenter at Wilson Creek to ferment and make VFAs? Okay, so we take them where we get them. Okay. And they've studied this stuff in the lab. And that's why I asked the question about fermenter operation. Sometimes fermenters are actually a part of the BNR design, where if there's not enough of these readily degradable carbon compounds naturally present by that's coming in from the collection system or through primary treatment and so on, then we actually manufacture them in the treatment plant by taking primary sludge, and we allow it to actually ferment and produce, basically make vinegar out of it. The PAOs are a number of species. Back in the early days, Acinetobacter used to be the one everybody said, well, oh, phosphorus accumulator, that's Acinetobacter. Yeah, well, it gets the credit because they could grow that one and identify it. Turns out it's really pretty insignificant. It's no longer the principal one. There are a number of others. They're heterotrophic, right? They're carbon lovers. They're facultative, obviously. They're switching anaerobic. They use readily degradable VFAs, and they store those. So that's your kind of repeat of what we've been saying. Even though you don't have fermenters, what this is illustrating is the fact that the rate of phosphorus release, then over time, the rate of phosphorus release here, comparing a BNR plant with a fermenter and without, is simply illustrated. You just get a more rapid release. The more rapid the release, typically the better it is for the PAO, because